So we just sooner we start, sooner we can go. Yeah. All right. So let me see. So for the next today to tomorrow, we will talk something about absorption and emission. This is the one of the basic aspects of photochemistry. So if you are interested in doing some sensor or doing some kind of reaction, it will be important to know about some basic principles about absorption and emission of elements. Okay? To understand the absorption and the emission, you need to know something about a molecule and also something about a photon. So these are the things which we talked about better. Okay, so when we wanted to think about a molecule, whether it is pyrene or formaldehyde or a big protein, the molecule is, we think, the most important thing about the molecule is electronic configurations. If you have a big molecule, not a big molecule, even a small molecule, to know the electronic configurations from zero level is impossible. So what we do is, we use the orbitals derived from hydrogen, that the Bohr orbitals, S, P and all those orbitals, that's what we use to build a molecule. When you think of a molecule, in an atom, the electrons are localized around an atom. In a molecule, the electrons are not localized around a molecule, so we call them as molecular orbitals. The way we build molecular orbitals is, we take the atomic orbitals and then mix them up, which is called as linear combination of atomic orbitals, LCAO. And what we get out of that is a molecular orbital. Okay, this is an assumption. We think it will work. It seems to work most of the time. So that's why we still believe in those things. Okay? And then when we want to calculate the energy of this molecule based on these orbitals, we assume there is no repulsion between electrons. That is the beginning. So what we get is not the right answer, but at least closer to the right answer. Okay? But the next step is, then you calculate based on the Born-Oppenheimer approximation, you fix the nuclear position and calculate the energy, and then you get rid of the repulsion. Eventually, you include the repulsion, and when you start including the repulsion, which is true, where the electrons are repelling each other, then we get two states, singlet and the triplet. And this is what we have done so far. So we have a molecule. When we think of a molecule, there are a lot of electrons. And those electrons are in different sets of orbitals. They are not all over the place. They are in very well-defined positions. Now, when the light comes in and interacts with this molecule, it is the electrons that are going to be interacting with the light. It is not the whole molecule as it is. It is the electrons that they interact. So, if you have electrons in a molecule, and then there is a photon coming by, and this photon and the electrons, they interact with each other. So this is, you can think of this as a wave, or you can think of this as a particle, because a photon can be both of those things. Similarly, the electrons in a molecule, you can think of them as a photon, you can think of it as a particle, or you can think of them as a wave. So both of them are confusing. Both of them are not very clear cut. It's not like, something simple like a water bottle. And it's not like that. So the water bottle, it could be a water bottle, or it could be like a cloud. So it is something that we don't know exactly what it is. So we sort of say it may be this, or it may be that. Okay. So the two electrons and the photons, when they interact, what happens? That's what we want to know. Okay. When the light is hitting on a molecule, what things can happen? When you think of a molecule, basically the electrons are the most important part of the molecule. It is not everything else. It is not the nuclear. It is the electrons that is going to be interacting with the photons. So When the light interacts with a molecule or any kind of materials, there are several things can happen. You might have studied these things in physics. When you take a course in elementary physics or general physics, you will. So when the light hits on something, it can reflect. So sometimes when you see a bright light hitting a road or some stone, then it gets reflected and then it hits your eye. Or it can undergo refraction. That means it can come and then it will get deflected and then go in a different direction. Or it can scatter. Scatter means if you have a solution containing some particles, if you shine light on this, you will see that the light gets sort of split into small, going in all directions, that is, gets scattered. But all of these things, the light has not disappeared. The photon that hits the material, it is still there. It has reappeared in different forms. Either it is getting reflected, or it is getting refracted, or it is getting scattered. The most important thing is the light that hits the compound or the material, it gets absorbed, it just disappears. That is what we call as absorption. So the photon that hits the molecule, they can get reflected, or it can go through, penetrate and then go through the other side. That is refractions. Or it can scatter into small pieces. But then another thing it can do is you just eat the whole photon, and if you eat the whole photon, the photon will go. And where it goes, what happens to the molecule, that's what we want to know. That is what we call as absorption. So, for example, if you have a light and then a prism, this light consists of different types of wavelengths. So, when you pass through the prism, it will diffract it into various, it will separate the prisms into various wavelengths. This is what the originally idea of Newton was. Basically, these different colors are coming from particles of different sizes. That's not true, that's what he thought. That's why he felt the lights are, the photon is a particle. Okay. Now, if you have, for example, when you see something, the white light that comes out of this projector, it contains all kinds of wavelengths, from 300 to 700 nanometers. And it is spread all over. But if you put a prism in front of it, then it will deflect all this into small, it will separate out all this blue, light, blue, yellow, red, and all this, it will separate out. Okay? Now, if you have, for example, the leaf, it is green. If you look at the orange, it looks yellow. If you look at the apple, it looks red. Okay? That is because what happens is the light, in the night time, none of these things has color. Apple or orange and all these things, they all have no color. But in the daytime, when there is light in the room, then each one looks different color. That is because what happens is the light that consists of all these various colors, say from the sunlight that comes in and hits the leaf, it will absorb some parts of it and leave out some of the things. Whatever is left out is the one that you see. So for example, this one has got a blue light, and then somewhat a greenish light, and then the red light. So the projector that comes out is going to have all of these things. If you have a leaf in front of it, the leaf will appear green. Why it appears green? Because all the other colors, the leaf absorbed. Whatever it did not absorb is the green, and that's the only one that you can see. So the leaf is not green. What you are seeing as a leaf is green. It is same thing with orange. Orange, for example, it absorbs all wavelengths except the yellow. So that gets reflected, and that is what we see. So the reflection, the absorption of the leaf is all these colors. Why some of them get absorbed, why some of them are not absorbed, that's what you want to know. Okay. So going back to the same old story, so these guys, the light, it must be absorbed. If you have something, if you want to see some phenomenon, if it is not absorbing, then it is basically reflecting the whole thing. So that's not a big deal. Okay. So this is So if you have, for example, you pass this light through a compound, through a molecule, whether it is going to absorb or not going to absorb, it depends upon the energy gap between the ground state and the excited state. Because when the light is hitting the molecule, it has to absorb it and use it for something. If it is not using for anything, it will just reflect the light. Whether it can use it, it will depend upon the gap between here and here. So this is the ground state and the excited state. So the molecule wants to go from here to here, it needs this much of energy. That much of energy is h mu. And the mu is c over lambda. Lambda is a wavelength. So this wavelength, if it corresponds to that wavelength, then that part of it will absorb. Whatever is not corresponding to that, it will just leave it out. So there will be a big gap. So if the projected light comes through and then you have a compound which absorbs the green light, then everything else is left out. If the green part is vacant, so the color will look very different. So the color that comes out of the projector will look not like going, it will look different. Okay? So, so that's why we spend all our time trying to figure out what is the energy gap between ground state and the first excited state. So the ground state is defined by these wave functions, and first excited state is defined by that wave function, and the gap between this and that is delta E, that is the E. Delta is this gap is energy of this, energy of that, so that is delta, that corresponds to h mu. So the molecule will absorb the light only that it needs. So it is not like, if it wants only $100, it will take only $100. Even if you put $200, it doesn't want $200. If you give him $50, it doesn't want it either. So if it needs 100, means it will take only 100. Okay. So this wavelength, that is the mu, which is actually c over lambda, that is what is going to decide where each molecule will have different gap. Because the gap between the ground state and the first excited state, that gap is going to change from one molecule to another molecule to another one. So some of them looks green, some of them looks yellow, some of them looks red, some of them looks black. That is because the absorption by the compound is changing, and that is changing because this gap is changing, and that gap is changing because the configuration of these or different electronic configurations of these things are different. Okay, so ground state, first excited state, and the first excited state basically, in the ground state there are two electrons in the HOMO. The first excited state, one electron here, one electron here. We talked about this before. Okay, absorption. How do you know a compound absorbs the light? So if you pass this thing through a beaker containing some compound, how do you know whether it is going to absorb or it is going to just the light is just going through? You can see that one. There is something called Beer-Lambert's law. Have you heard of this? Beer-Lambert's law? Beer is not the beer that we drink. It is the guy's name. Beer-Lambert's law. Basically, absorption is the intensity of the light that you put in and the intensity of the light that comes out. So if you pass, like if you push through $100 bill and then somebody is sitting here, the $100 completely comes out on the other side, that means he didn't take anything. So if you put $100 and only $80 comes out, this guy took $40 from you. So that is called absorption coefficient. How much light that compound is absorbing is measured by the absorption coefficient, which is controlled by some couple of factors. These are the factors that we want to know. Okay? So it depends upon what is called as extinction coefficient and the concentration and the length of the cell. So usually you take the absorption spectrum of a compound. So you take a small cell, fill the cell with the liquid, and then put it in the spectrometer. Light will come through, the light will go through. Okay? if this molecule, so we are going to push light from 300 to 700 nanometers. The molecule wants only some 800, so like this 500 nanometers. So the light 500 goes through, that will absorb. 300, 400, and then 700, 900, it will pass through the sample. Okay. So whether the 500 is absorbed, how much it is absorbed, is measured by this extinction coefficient. Why it absorbs at 500 but not at 300, or it doesn't absorb at 600, it is, we want to know. And then what is the probability of absorption? If the light is going through, is there 100% chance everything will get absorbed, or maybe 10% chance things will get absorbed? So that is all controlled by this parameter here. It is called extinction coefficient. So the extinction coefficient for a particular transition varies from molecule to molecule and the type of transitions. Okay. So the overall, if you want to find out the absorption coefficient, is also called optical density. Optical density means, so if you push light through a compound, if all of it is absorbed, the optical density will be close to 3. That is, for example, 2. That means only 1% of the light that you pass through is getting transmitted. Optical density is 1, 10%, 0.01 is 98% of the light is passing through. Okay? So it will change from molecule to molecule. So why does it change? For example, when you take the absorption spectrum, how many of you have recorded the absorption spectrum of any compound? No, the department must have UV visible absorption spectrometer, and then you probably have taken some absorption spectrum. How many of you have taken absorption spectrum? Or at least read something about absorption spectrum? How many have taken absorption spectrum? No? Nobody? No one has taken absorption spectrum? Somebody who is doing, work with after leaping. So, okay. They must have taken absorption spectrum, or at least looked at the absorption spectrum. Okay. So the absorption spectrum looks like this. Okay. It looks something like this. For somebody who is walking in, the downtown, this doesn't mean anything. And for you, it should mean something. What it says is, this side is absorption, this side is wavelength. If the compound is absorbing the light, then you will see the line is going up. If the compound is not absorbing the light, it will be completely zero. Okay. Or the other. So what happens is, you have the light is going through, you have a sample, and then you find out on the other side, you measure what the light that you put in, what light is coming out. So you plot this with respect to wavelength, and the plotting, if the compound is absorbing the light, the wavelength that passing through, it is not going to appear on the other side. Okay? So when it is not appearing, that means we are plotting this as absorption. As you see here, in this region it is low, some places it is high, and some places very high. So, for example, this molecule, whatever it is absorbing between 450 to 570. So that's how we decide. You take the absorption, the light that you're pushing through, it has from 300 to 250 to 700 nanometers. When this going through the sample slowly, so if it is absorbing around 350, that means you will see on the other side zero light coming out from 350. If it is not absorbing at 550, other side all the 550 will pass through the sample. Okay? And so you can record a spectrum like this, wavelength and absorption. Or the other approach is, depending on the instrument, you can measure the transmittance, how much light went through the sample. So when everything goes through, the transmission is 100%, that means it is not absorbed. It is exactly opposite of the spectrum here. This is, it measures the absorption, it measures the transmission. Transmission is something passing through. Absorption is something that is absorbed. Okay. If you look at the absorption, the wavelength, if you look at this, each book will provide absorption spectrum. But the way it looks will be different for the same compound. So it depends upon, for example, this side is on this side, The wavelength is plotted in angstroms. So there are different units for the wavelength. Wavelength is basically the distance between the two peaks. You can measure in angstroms, you can measure in nanometers, or you can measure in kilohertz. So all these things, depending upon how you measure the plot this stuff, it will look different. They are all the same compound, but as you see here, each one looks different. So you should not get alarmed. You have to look at the axis here. This axis is very important. In this case, is centimeter minus 1. In this case, it is Armstrong. And then in this case, again, it is Armstrong. So it will vary. It's not a big deal, but if you have an instrument and the spectrum for you and for somebody else may look different, but it has the same information, but it is plotted very different. Okay. So, for example, here, if you have a double bond, carbon-carbon double bond, it will absorb at 180 nanometers. Okay, we said all these things in terms of kilocalories and all these product of finding out how much is the gap. So that gap is going to be useful here. What we calculated using this Born-Oppenheimer approximation and all these things, we said S0 is this much energy, S1 is that much energy, and that gap is what we are talking here. That gap is the one that is going to decide where the compound is going to absorb. Instead of saying things in kilocalories, you will say them in nanometers, wavelengths or angstroms. So double bond 180, and then diene 220, a triene is 260. So depending upon the molecule, where the compound is going to be absorbing is going to change. So this is very useful. If we have a solution of benzene and another solution of anthracene, the absorption will not be identical. They will be different. Okay. That is because if you remember, when we said the energies of these molecules, a double bond. Okay, let's say for example, you take benzene. It is going to be a 0, and then it is going to be S1. And then if you take anthracene, this is S0, and then it is going to be, first one is going to be S1. So if you look at this gap, and then if you look at this gap, this one is smaller, that one is larger. So if you want to take an electron from here to here, it requires only this much energy. Whereas taking an electron from here to here, it requires more energy. And this is what we said, for example, the more the conjugations, the orbital energies are closer to energy, and then it becomes. So you can see here, for example, in benzene, the absorption is 260 nanometers, and anthracene is 380 nanometers. These things you can find in the book. You don't have to remember all this stuff. Okay. So, for example, this is plotted in nanometers. The same number would be in wavelengths in the angstroms. Tell me which one is more energy, 260 nanometers or 380 nanometers? Which one has got more energy? Energy is h mu. So, taking S0, S1 for anthracene, it requires less energy. So, the molecule will take only that much energy. So, if it wants only 50 kilocalories, and then if you put 100 kilocalories, you are not going to make it faster. It doesn't take that energy. So, the gap is, in anthracene is smaller and benzene is larger. So, if you have an absorption spectrum, what will happen is, the gap corresponding to S0 to S1 will be absorbed, and then everything else will not be absorbed. Similarly, for example, benzene, it has a larger gap. So corresponding wavelength will absorb, and everything else will not be absorbed. So that is very important to know. It is just because you have the gap is 50 kilocalories, you think, okay, I will make this reaction go faster, or I will get a stronger emission by putting 150 kilocalories. then it will not happen. The molecule will not take 150 kilocalories. It wants only 50, and if you put 50, it will absorb it. If you don't put 50, it will not be ready. So another question is 260 and 380. It is a wavelength, nanometers. Which one has more energy? Which one has more energy? Huh?
More.
Which one?
Benzene is need more energy.
Benzene needs more energy. Okay, that's the picture. So which one has 260 nanometers or 380 nanometers of that? 260. Okay. So in terms of wavelength, is that something that also you have to know? Wavelength is lambda. You can also represent this by frequency, which will be 1 over lambda is frequency. Sometimes you will see this stuff. But you don't have to worry about it now. Okay. And you can see on the other side what is called as extinction coefficient. I mentioned it to you. The probability of absorption, the energy that is required, if you put 380 nanometers through the compound, it will absorb. It needs. Whether the probability of absorption, how, if you put 100 photons, whether it will absorb or not, it depends upon the extinction coefficient. It needs 200, 380 nanometer light to go up. Whether it will use it or not will depend upon this particular number here. For example, anthracene is 10,000. 10,000 means is good. And then if you take benzene, it is 200. That means it's not that good. It needs 260 nanometer light for it to go from S0 to S1. So it gives the energy, but still it is not able to take it because the transition, whether it is allowed or forbidden, will decide whether it can give the energy, whether it can take or not. So that part of it is what is called the selection rules. Okay. So that number will decide how efficiently you can activate a compound. So for example, here, this number is all over the place. 1,000, 10,000, 40,000, 20, 30, like that. But the wavelength, it tells you the gap between here and here. That gap is, for example, benzene is 260, for this anthracene is 380. But then, if you put 260, whether all the benzene will go up is questionable, because the extinction coefficient is only 200. The probability of absorption is very small. Whereas for anthracene, it is 10,000. That means when you put 380, there is a good chance the light will be absorbed in the sample. Because when it absorbs the light, the electron has to go from one orbital to a different orbital. Whether the photon can do it will depend upon some factors which we will talk about. They are called as selection rules. There are some rules which tells you whether if you put just exact amount of energy that is needed, whether things will happen or not. It is like putting some money into the vending machine. You put $10 bill, you want to get something. You put $10, sometimes it comes down, sometimes it doesn't come down, because this machine is not working properly. Okay. Okay. So the ground state, and then when you excite it, if one electron goes up here and one electron goes down there, these are the various things. So whether the electron will go from here to here, it depends upon these things here. We go back to the same old story. So the transition is basically going from here to here. Whether when you put the energy, whether it will go from here to here, will depend upon the electronic configurations, the spin configuration, and the vibrational configuration. So all these three defines a molecule. When you say a molecule, it is vibrations, spin, and electron. Where exactly all three? These are in the ground state. This is in the excited state. Whether it can go from here to here, if you provide the energy, it will depend upon whether this and this will match, and this and this will match at all these states. So they have to match. If they don't match, even if you give the energy, the molecule will not go to the excited state. We need to figure out how to know what is matching, what is not matching. That is what is eventually is going to control whether if you put exactly enough energy, whether it will go up or not. If everything is perfect, this is perfect, that is perfect, we don't put enough energy, it will not go. Energy is important, but more, the second part is knowing whether the transition is allowed or forbidden. There are two types of. Something is called allowed, that means everything is great. Something forbidden means everything is bad. You have S0, you can see S1, but this molecule doesn't want to go from here to there. Even if you put any energy, it doesn't want to go. Then you just have to figure out how to make it go up. That's a different problem. Okay. All right. So here, this is the way the spectrum for some molecule looks. Okay, normally, if the transition is allowed completely, right? You can see here, this is 1, and this is 2, this is 3, and this is 4. All these things are, for example, the wavelength is on the bottom. The wavelength is in nanometers. So when you go from this end to that end, the energy is decreasing because the wavelength in nanometer is increasing. The higher the wavelength, the lower the energy. So now what happens is, if you pass light through, for example, this contains something, and the light comes through. The light that is going through is going to have wavelengths all from 200 to, let's say, 700. So when the light is going through, it will absorb some of it it will not absorb. Whatever it needs a gap, that's the only thing that will absorb. So if you have, for example, S0 to S1, S0 to S2, S0 to S3, the gaps are different. Okay? So you can see here, S0 to S1, you see the absorption. S0 to S2, that is going from here to this state, there is an absorption. Going from S0 to S3, there is another absorption. So the gap between S0 to S3 is large. So it needs a shorter wave. Going from S0 to S2 is a little less. It needs slightly longer wavelength. Shorter wavelength, longer wavelength, S0 to S1, the gap is even smaller, then it is going to be even longer wavelength. So the absorption that you see corresponds to 3 different states, S0 to S1, S0 to S2, S0 to S3, and each one comes up in different wavelengths. But if you notice, the absorption, that means if it is all over here, the higher it is, the good. That means the higher the peak, that means the probability is larger. If the light is going through, and then if everything is getting absorbed, that means the signal is going to be somewhere here. If it only little bit of it is getting absorbed, most of it is coming out, and it is going to look like this. Okay. As you see in this picture, the absorption for S0 to S1, S0 to S2, S0 to S3 are not identical. Okay. If identical, you will have a spectrum like this. Everything will go to the same height. But obviously this is high, pretty high, medium, smaller, and the other one here which is tiny. Okay. So this is controlled by the exclusion coefficient. So smaller the exclusion coefficient, the absorption is going to be bigger. So this, for example, if you look at this here, this is log epsilon. Log is plotted in the log scale. This is a very small number, that is somewhere here. And this one is somewhere here, that is 1. And this one is approximately 3. That one is 5. That is 10 to the power 5, 10 to the power 3, this is about 100, and this is almost 1. So the exchange coefficient is 1. So for each transition, it is different. Why it is different? Because the molecule going from S0 to S1 involves the electronic transition from one orbital to a different orbital. But the orbitals involved between all these transitions are not the same. They are different orbitals. So since they are different orbitals, the rules are not exactly identical. If it is identical, everything will be flat, 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 flat. 10 to the 5, 10 to the 5, 10 to the 5, 10 to the 5. So now it's not like that. So now the question is, why this absorption is weak, medium, and very strong? Although this absorption looks it requires a lot higher energy, S0 to S3, it requires a lot of energy, but that molecule wants to go to that state much more efficiently than going to S0 to S1. It is much smaller energy. So energy is not criterion. It is basically whether the electrons can go from one orbital to another orbital. That is the main criterion. So if whether it requires 50 kilocalories or 100 kilocalories, just because it requires 100, that doesn't mean it is going to be weaker. So whether 50 is going to be strong or weak will depend upon what type of transitions we are talking about. Okay? So, any questions? Any questions? No questions. Okay. Now, okay, we'll talk for 5 more minutes to finish up. Okay. So whether the absorption that is going to S0, S1, S2, S3, whether it is going to happen or not, it is going to depend upon, this is basically electronic transitions. We are talking about electrons going from one orbital to another orbital. For the electrons to go from here to here, we give the energy. The energy is coming from the light. But that is not sufficient, because the electron will have to find a way to go from this orbital to another orbital. Whether it can find a way to go from one orbital to another orbital will depend upon the two orbitals that are involved in the transition. Okay? So, that one is called as oscillator strength. Whether a transition is allowed or forbidden is controlled by some factor, what is called as oscillator strength. Oscillator strength, if it is 1, that means 100% perfect. If it is 0, that means bad news. Everything is poor, nothing is going to happen. So depending upon, for example, the transition, the oscillator strength can change. Whether that is with the electronic, that means whether the two orbitals are involved in the transition. If it is symmetry and the overlap between the two orbitals, will decide whether the particular transition is allowed or forbidden. The other one is going to depend upon the positions of the nuclei. And the last one is going to be dependent upon the spin. Because when the electron is going from one orbital to another orbital, if the spin is not going to change. If the spin has to change, then that particular transition is going to be very weak. Similarly, if you remember, we said that during the vibrations, when the transitions, electronic movement and the movement of nuclei are of different time scales. So when the light hits the molecule, the electron is immediately going to go from one orbital to another orbital. That is about 10 to the minus 15 seconds. So at that time, the nuclear positions are going to be fixed. If the transition requires a change in the nuclear position, that means that has a very poor probability of happening. So at the end, all these three are going to be electronic, vibronic, and spin. How these are positions, S0 and S1, how they are with respect to each other, that will decide whether a particular transition is going to be allowed or forbidden. The energy wise is known, say 0 to S1, let's say 100 kilocalories. You can give 100 kilocalories to your projector. Whether it will take it or not will depend upon 1, 2, and 3 factors. Whether all these factors are working out, now you have to know more details about S0, S1. That's what we try to see from various, using the Born-Oppenheimer approximation, we figure out the electronic configurations of the states, the spin configuration of the states, and all those things have become very important. Okay? I think I will stop here today. Okay, so now you can go and read and then come back tomorrow. Okay? It's over.